Okay, in this video I'm going to review some of the example problems that I skipped over in class on Friday night, just to give you an idea of what those are all about. Didn't give you any homework using the closed thin wall tubes or the open thin wall tubes. We'll still look at it anyway. And so we of course have the equation TR over J if things are circular, but what if we have a closed thin wall tube that's not circular? This one is showing more of an elliptical shape. And that basically says that if we understand the shear stress flowing around this tube and a uniform shear stress flowing around this tube, we can basically sum the moments and relate the shear stress to the total torque by integrating. And it turns out that what we end up integrating is this quantity dA right here. We end up getting the area all the way around the circle. So looking at an example, we saw the formulas in class. So we have a welded steel tube, 40 inches long, 1/8 inch wall thickness, 2.5 by 3.6 inch rectangular cross section, as shown in Figure 3-26. Assume an allowable shear stress of 11,500 and a shear modulus of 11.5 million. Estimate the allowable torque and estimate the angle of twist due to torque. And so our formula, which relates the torque to the shear stress, is the torque is equal to 2 times the area, we'll talk about what that precisely is, times the thickness, wall thickness of the tube, times the allowable shear stress. And the area is if this were a pure, whatever the shape is, imagine a line right through the middle of the thickness everywhere, which would be another ellipse, and then imagine the area inside that line. That's what we would be computing. So for a rectangular tube, we're going to calculate the area of a tube, which is of cross section. The area is 2.5 inches minus half the wall thickness. And for, let's see, actually 2.5 inches minus an entire wall thickness on each side, and 3.6 inches minus an entire wall thickness on each side. And so, let's see, our area then, did they give us the area? They didn't compute it out, but it's going to be something close to, it's going to be very close to 2.5 minus an 8 multiplied by 3.6 minus an 8. Ought to get that number, and what we get for the allowable shear stress of 11,500 is a 23,730 inch-pound force torque. That seems like a pretty good torque. Then what's the angle of twist? And our formula from the previous page was our angle of twist is the torque times the length of the shaft times 4 times G times that same area times the allowable shear stress. Here's our torque, our length of 11.7. What were we given in the length? Were we given 11.7? 40 inches. Okay, I've got this L sub M thing. Yes, L sub M is not the length of the tube. It is the perimeter section of the medium line. Then this must be, since the length of the tube never comes into it, is this the angle of twist per unit length? And I don't see that defined. That puzzled me for a moment, almost caused me to make a mistake. So let's see what we find out about this thing. I may have to start over. Okay, the total theta, here it is. The total theta is the theta 1, which would be a theta per unit length, times the overall length of the part. And notice over here they put a 40 in as the overall length of the part. And then this is the length of that mean line. That L sub M right here is the length of the perimeter of A sub M. Okay, and again, adding up 2 2.5s would give us a 5, and 2 3.6s would give us a 7.2, and so a 5 and a 7.2 would be a 12.2, but we're a little bit less than that because we have some 1/8 to subtract, so that probably does come out to be an 11.7. I didn't compute that precisely, but our theta 1 angle of twist per unit length is everything here except the 40. L is 40. Crunching that number out is 0.0284 radians, or 1.62 degrees. Not a very large deflection for what is a pretty incredible torque. And that ends, let's see, no, it doesn't end this discussion. We then go to open sections, as discussed here. We have a equation that relates the shear stress and the torque, and we have an equation that relates the shear stress and the angle of twist per unit length. Okay, and let's see how that works out. Let's look at an example. Okay, example illustrates one thing, but it doesn't illustrate the most important thing. So we have this 12-inch long strip, 1/8 inch thick, 1 inch, I would call it tall, and 1/8 wide. He said it differently. If the allowable shear stress is 11,500 and the shear modulus is 11.5 million, find the torque corresponding to the allowable shear stress and the angle of twist in degrees using equation 3-47 and equations 343 and 44, which were earlier in the textbooks, which were approximations for rectangular sections. So we're going to compare the correction, which is a bit more sophisticated. This ought to be the better answer to our very simple approximation. We'll see how it turns out. Now, my note here that says this isn't the best example, because what it doesn't show is how that tiny slit right there in that circle absolutely ruins its ability to carry torque. So we'll look at that in just a second. And so for this one, the length of that median line is the overall height of this part right here of 1 inch. And the thickness is of 1/8, and that's called C. Okay, so the length, 1, thickness 1/8, and that's squared. The allowable shear stress, 11,500 divided by 3, would be a 59.9 inch-pounds force of torque that can be carried to bring our stress up to an 11,500. And then our equation for the angle of twist is that the angle of twist, theta, is equal to theta 1, which is twist per unit length. It says times TL over GC. I just want to go back and check that equation. Yes, okay, we have G theta C. There's no L in this equation. We brought the L in because we're referring to the total theta, not the theta per unit length. That's where this L comes from. It's that L right there. Plug in the numbers and get 5.5 degrees of twist. Okay, now, I don't think they said it in the problem. Did they say calculate a torsional spring rate? Okay, well, a spring rate is going to be a spring stiffness for a linear spring would be pounds per inch or something like this. And spring rate for a rotational system would be something like inch-pounds per inch or something like that, or torque per radian in this case, if we're not going to go with degrees. And so our spring rate is the torque divided by the angle of twist in radians in this case. And we get a 624 inch-pounds of torque per inch. Our radian is inches per inches. Okay, using the older correction factors, we'd have to go back and read that table, and that table involved B and C, where B was the bigger of those two dimensions, and so our B is 1, you can see it here. Our C is 0.1125, and we have a B over C, a 1 over 0.125. And plugging in all the other numbers, we get a 55.72 inch-pounds force as compared to 59. I'd call those pretty close, reasonably close, although this is probably the better number. And then using equation 3-44, and we have to look up the value of this quantity beta from the table. Okay, and so beta being 0.307, go check that for B over C equal 1 over 1/8, which is 8. You can go check that beta value. Just plugging everything else in, we get a 5.6 degree angle of twist, very close to the 5.5, and a slightly different spring rate, 574 as compared to 624. Okay, that's probably not what's most interesting about these equations. Let's go look at something else. Okay, and I don't have any great picture here. What I have is a thin wall circular tube. That circular tube has a 1-inch outer diameter and a wall thickness of 0.05. Therefore, it has an inner diameter of the outer diameter minus 2 times the thickness, or a 0.9 inner diameter. And let's see, our radius that we're going to use, the outer radius, maybe I should have called that RO, is DO over 2. And the torque that I'm going to apply to this thing is a 1,000 inch-pound torque. Now, first of all, I'm going to use the circular formula TR over J, where J for a hollow circle is pi d outer to the 4th over 32 minus pi d inner to the 4th over 32, giving us a value of J. And when I calculate a shear stress equal to TR over J, where T is that torque of 1,000, I get a 1481 times 10 to the 4th, or a 14,800 pounds per square inch shear stress. So almost 15,000 psi shear stress. Now what I want to do is use the thin wall closed formula instead of TR over J and see how that turns out. Now the closed formula says calculate the area inside that median line. In this case, the area inside the median line is an area of a circle where the diameter of the circle is halfway between D inner and D outer. So here's the average of D inner and D outer, DI plus DO over 2. Then pi times that diameter squared over 4 is that area. So I call this one T star, the torque. That would be given by our 2 A sub m thickness times tau. And what we get for a torque using the same tau that came out of the other problem. So I'm sort of, from one I went from torque to shear stress. This one I'm going to go from shear stress back to the torque. And what I find from this formula is that the shear stress that came from TR over J produces a torque of 1,050 inch-pounds. Okay, it's a pretty small difference compared to the 1,000 inch-pounds that I started the problem with. So that's actually in pretty good agreement. Now the question is, what happens if I put a slit on that thin wall cylinder and ruin its ability to carry torque? Let's calculate the shear stress that would come from this 1,000 inch-pound torque. And that formula 3 times the torque over the length of that mean line times tau squared, and the length of that mean line is pi times the average, pi times d, which is, and d is the average diameter, which would be that median diameter. And so come up with a tau value of 400,000 psi. Much higher stress because of the shear stress, much higher shear stress because of the slit, which has reduced the ability substantially of that material to carry torque. And so that illustrates the difference between actually 3 different methods. TR over J works great for circular things, probably the gold standard. The approximation for closed thin wall tubes, right here, and then the approximation for open thin wall tubes to demonstrate how bad an open circular section can be. And that would end this video.